about different functional groups from here on out for the rest of the semester. This chapter is about alkyl halides, and then we'll have a chapter about alcohols and ketones and aldehydes and so forth and so on. And basically what we're going to be doing at this point is talking about chemistry that carbon can do. We've so far have talked about structure of carbon. We've talked about stereochemistry and Newman projections and Lewis structures and acid-base properties. Now we're going to get into the reactivity. Now that we know all that stuff, let's start getting into the reactivity, start talking about how carbon reacts and how to synthesize specific compounds. All right, so like I said, this chapter is going to be alkyl halides. There are several classes of alkyl halides. This is just, this one is just, an sp3. It's called alkyl halide because it's all sp3 carbons with a halogen on it. Vinyl halides have a double bond on it. Vinyl, everyone's heard of vinyl, the chemical or the material, and it actually comes from a double bond, which is where that vinyl term comes from, is from a compound that has sp2 carbons in it. And then you have aryl halides, which is basically an aromatic ring that has a halogen. Now, these are still all called alkyl halides, but if you want to get more specific, instead of calling a vinyl halide alkyl halide, you call it vinyl halide and aryl halides because it has a benzene ring. All right, polarity and reactivity. We know that the halogens are generally more electronegative than chlorine, so this partial negative charge on the halogen, making the carbon very partial positive charge. Well, anytime you have this unequal sharing of electrons, you technically have a possibility of reactivity, which is what we're going to start seeing over and over again. That's why we learned about what makes a Lewis acid, Lewis base, what's partial positive, partial negative. So this carbon that has a partial positive, you can add some sort of nucleophile to it. Remember, nucleophile has a negative charge. You can add to them because it has this partial positive charge. So because halogens are more electronegative than carbon, carbon-halogen bond is polar, so carbon has partial positive charge. We just talked about this. Carbon can be attacked by a nucleophile, everything I just said. And halogens can leave with their electron pair. Halogens, so basically the reaction we're going to talk about is we're going to have some sort of a nucleophile, all right, something with lone pairs and a negative charge. It's going to come in here and start forming a bond with carbon, kicking out the halogen. The halogen is going to leave with the electrons. First, let's talk about some naming. There's nothing tricky or special here. We've already talked about this. Naming alkyl halides. Alkyl halide is not a parent chain. Your longest continuous chain of carbons is the parent chain, and you call it an alkane. And then you just use fluoro, chloro, bromo, or iodo. Okay, so there really is no special case here. Here's a compound, pretty simple. The second carbon has a chlorine, so this is 2-chlorobutane. Okay, nothing weird here. Here are some examples. All right, start numbering it again on the side closest to the nearest substituent. So 6-bromo-2-methyl nonane. Here you have a cyclohexane. You've got a bromo and a fluoro. Bromine alphabetically comes before fluoro, so that's going to be your 1 carbon. And the fluorine is going to be your 3 carbon, so 1-bromo, 3-fluorocyclohexane. Okay. Oh, in this case it's cis because we're showing you stereochemistry. Okay. Here's some common names. Isobutylbromide. This one is sec-butylbromide, tert-butylbromide. These are just common names, not something you need to know. Don't worry about memorizing this. I'm just kind of bringing it to your attention that these compounds are so common that they have a name specifically for it, rather than naming it, like 1-bromo, 1-methyl propane. Just call it sec-butylbromide. Here's some common alkyl halides. Methylene chloride we've used, methylene chloride we've used in lab, called dichloromethane is another name for it, DCM. So for this methylene chloride, DCM was you remember we used that when we did the extraction of tea. We used DCM, dichloromethane. It's called methylene halide because if you have bromide, it'd be, instead of methylene chloride, methylene bromide, methylene iodide. If you have 3 halogens on 1 carbon, it's called a haloform. So like that compound would be called chloroform or bromoform or iodoform, depending on the halogen. You've heard of chloroform. It's used as an anesthetic, or it was used as an anesthetic. Carbon tetrahalide, so if you have chlorines, it's carbon tetrachloride, carbon tetrabromide. All right, so common solvents, methylene chloride, chloroform, carbon tetrachloride. So there you go. Classifications, you have a methyl halide. It's basically a methyl group with a halogen. You can have a primary alkyl halide where you have one carbon attached to a carbon that's attached to the halogen. Secondary, 2 carbons. Tertiary, 3 carbons. Here they are. So methylene chloride, you have a methyl group attached to a halogen. All right. This is primary. You have a carbon attached to one other type of carbon group attached to the halogen. Kind of a little better. The way I kind of like writing them is like this, so if this helps. Okay, so here's my carbon. This is a primary carbon because it's attached to one other carbon and the halogen. This would be attached to 2 carbons and your halogen. And then this one would be attached to 3 carbons and your halogen. All right, types of dihalides. These compounds just have general names. So if you have 2 halogens on the same carbon, it's called a geminal dibromide. If you have halogens next to each other, it's called vicinal. All right, so geminal on the same carbons, vicinals where the carbons are adjacent to each other. Some uses: industrial and household cleaners. Some uses, I don't really think it's that common as a household cleaner. These are kind of carcinogenic, so I'm going to have to look that up to see if that really is true, but maybe in industry I can see that. Anesthetics, anesthesia. Chloroform is used for a long time as a anesthetic or an anesthesia, but again, it's toxic and carcinogenic. Halothane was also used. I think that actually still might be used in like a little mask, just to kind of knock you out a little bit. Freons in refrigerants and foaming agents, as far as in a fire extinguisher. They do harm the ozone layer, so we're trying to get away from that in our refrigerators and our air conditioners. Pesticides, DDT. It's a pretty big molecule with a bunch of chlorines on it. Great for killing insects. However, it is toxic to mammals because bacteria does not break it down. So when it gets into the soil, it stays in the soil. So when you start plucking your food out of the ground, you have all these pesticides all over the food. That's why you should wash them very well. Boiling points. Boiling points are relatively high because you have dipole-dipole forces. Relatively high compared to hydrocarbons. They're still, they're not as high as compounds that form hydrogen bonding, but because of the dipole-dipole attractions, they have pretty high boiling points. It doesn't matter if it's chlorine, bromine, fluorine, iodine. It doesn't matter. It's not like one halogen makes a bigger difference than other ones. They pretty much are pretty much the same. London forces are greater for larger atoms. We know all this. Greater mass, higher boiling point because you have greater surface area. So here's an example where you have a straight chain that boils at 102 opposed to a very branched chain which boils at 73. Densities. Densities for the most part of halogenated solvents are more dense than water. There are a few exceptions where that is not the case. This is a little weird how this came up. Alkyl fluorides and alkyl chlorides, where you just have one halogen, are less than water, so they float on top of water. But if you have more than 2 chlorines or a much larger molecule, most of the bromides and iodides, those are going to be more dense. So for the most part, most alkyl halides are more dense than water. All right, that was some properties. Let's now start talking about the preparation, the synthesis of alkyl halides. Some of the common ones that we've talked about is free radical halogenation. These are kind of the common ones. All right? Remember, chlorination is not very selective. It produces a mixture of products. But remember, bromination is very highly selective. It goes for the more substituted position because you form the more stable radical. All right, we're also going to talk about allylic halogenation. We've talked a little bit about it in the lab. We've talked about allylic and benzylic as well, where the halogen is placed directly adjacent to the double bond because of resonance. All right, so halogenation, these are reactions we've done. You can take chlorine plus light. H nu is a symbol for light. Remember, E equals H nu from your Chem 111 days. All right, or you can take bromine, and bromine's going to go in the more substituted position. Chlorine's not very selective. Bromine, though, selects tertiary carbons over secondary over primary. Allylic. The allylic position, as you can see, are the positions right next to the double bond. All right, so when you brominate, you're going to brominate right next to there. And remember, the reason is because you form, when you form a radical, so imagine a hydrogen gets plucked off, your intermediate, oh, that is just awful. Your intermediate is going to be a radical right here, right next to an aromatic, a double bond. So you can technically draw a resonance structure. All right, that's a resonance structure of a radical. So because it's resonance stabilized, your bromine is going to go in that position. Okay, so allylic radicals are resonance stabilized. Bromination occurs with good yield at the allylic position. All right, the mechanism, we've talked about this mechanism before, but as we'll go through it again, the bromine plucks off a hydrogen, giving you that radical. I just did this previous page, not as much detail. And then that radical, because it's resonance stabilized, is going to react with the bromine to form your allylic bromide. All right, the mechanism involves an allylic radical stabilized by resonance. Both allylic radicals can react with bromine. All right. The other thing I want to talk about is benzylic. These slides don't have anything about benzylic, but benzylic is if you have an aromatic ring, and remember, it's the carbon adjacent to the aromatic ring. Same thing. You can add a Br2 and H-nu and brominate this position right here at the benzylic position. Remember, benzylic is a special kind of allylic. All right. If you think about it, it really is allylic. It's I have a double bond here, all right, adjacent to a carbon group. So that's kind of the allylic part of it, but it's a benzylic. So you can do the same exact thing. Bromine is kind of nasty. Bromine is expensive, it's toxic, it's hard to use, it forms hydrochloric acid, it's a liquid that has this fuming bromine on top of it. So they've come up with a different compound called N-bromosuccinimide. For short, we call it NBS. It's a much more user-friendly chemical, not as expensive. It's a white solid. You can weigh it out. It doesn't fume. It's not that toxic. And what it basically does, so here's the structure of NBS right here. This is it right here, N-bromosuccinimide. The name comes from N, the nitrogen, bromo. The bromine is attached to the nitrogen, and then this part of it is called succinimide. All right. What it does is, in a little presence of hydrobromic acid, you actually form bromine in situ. So what that means is in the reaction, it's starting to be produced as the reaction is going. So you have very low concentrations of it, and it's actually very useful as a compound. So NBS is mostly used allylic and benzylic. Again, I'm adding the benzylic part of it. Oop, 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 oop. I'm hitting buttons. Benzylic. Okay, so use NBS opposed to bromine, much better reaction. It keeps the bromine concentration low. So here's just some examples. All right, here you have allylic positions right here. So that's the you actually have 4 equal allylic positions, but it's going to brominate. We'll talk about things like this. This is a rearranged compound. That's kind of interesting, but we'll talk about that in a little bit. Okay, so that's basically how you make halogenated compounds, mostly from radicals. You can do allylic and you can do a benzylic. All right. The remainder of this chapter is about reactions with alkyl halides. Once you've made the alkyl halide, what are you going to do with it? And we're going to talk about very 2 important reactions. Those are nucleophilic substitution reactions and elimination reactions. And we will start that on the next video.